There was an announcement on Monday for a new Azure service called AzureML. It's a fantastic system, and all of the demonstrations that I'm going to show you today are so much simplified by AzureML that it's unbelievable. It's a very interesting, holistic environment which understands Azure. So it understands things like HD Insight and blob storage and SQL Azure. And being able to put all of these building blocks together and just slot the machine learning piece in so that it's one component of a big data system is a really, really powerful thing, because at the moment, to put these things together is quite a chore. They're very, very disparate. So I've been doing quite a few talks around not being a data scientist. I meet a lot of data scientists with the work that I do, and also when I evangelize and talk about big data systems. And some of these people are absolutely fantastic mathematicians. As a show of hands, any data scientists in this room? So there's only possibly a pool of two, since two of you have used machine learning in the past. And actually, I don't know why I asked that question, because I know that both of you aren't. So there's a lot of dictionary definitions about data scientists, and the fact that I think the best one that I've heard is they know. Oh, forget it. I'll put it on there. It's a sort of a data scientist is a hybrid between a statistician and a programmer, but the claim is that they can't do statistics as good as a PhD mathematician, although many that I've met can, and they can't code as well as a programmer. So what I would say is that in a very, very hacky way, data scientists actually train to do small-scale systems. So using languages like Python and R, very, very much desktop-oriented. But all of the problems start when they take these models out of the desktop domain and then put it into a production domain. That's where everything falls apart. So my real feeling about this is, as developers, we're going to fall more into this space, and we're going to understand the types of things and scenarios that Dave was talking about, because big data is going to be central to everything that we do. With all of these cloud resources around and all of these buildings of intelligent systems, we're going to fit more into this model where we have to take everything that a mathematician does in determining, how to put these predictive analytics together and make it work. And in order to do that, we have to understand a little bit of the maths, but we have to understand more of the software libraries. So we'll look at some of the software libraries today. So I'm going to take you through some things, and these are a couple of definitions around recommender systems. So we see a lot of these recommender systems online, and what I wanted to do is give you a brief background on how they're actually made and the thought processes, and what I have to do as a developer to then take a whole bunch of data and then present that back to the user in a few images or books that they want to buy, or videos and movies, with levels of accuracy that Dave was talking about, those sort of high 80% or 93% confidence levels. So there's a couple of definitions we'll talk through. That the idea of a recommender system is to use the opinions of a community of users to help individuals in that community identify more effectively the content of interest from a potentially overwhelming set of choices. Make sense? Okay. And then we've got another definition as well. These definitions really, really hone in on the fact that when we talk about being able to deliver recommendations to users, we've got a potentially huge set of users. Imagine this volume, this data set volume, the number of users and customers that companies like Amazon have or Netflix have. How do you begin to process that amount of data? How do you begin to process the amount of data that the movies or the books that they've bought or rated or looked at? It's a very, very difficult problem space, and it doesn't just need one technology, it needs a set of technologies to pipeline and to shrink that down. Then you've got the added complexity of machine learning. Anybody remember Newton-Raphson from school? O-level, GCSE, come on. Okay, statistics. Iterative method, right? What do we know about iterative methods? They're very, very compute intensive. That means that if you have a huge data set and you have a very, very compute intensive process, you're going to need lots of virtual machines to do things. And this is where the conversation about the cloud, distributed computing, Hadoop, all of these big data platforms actually come in. Okay, so I'm going to run through a few slides and not go through so many definitions with this. But I want to give you an idea, I want to give you a sense of what this recommendation system actually is. So it comes from a process called collaborative filtering, which pretty much is, as it says, where users, we do things on a website, with any system, and we have preferences. And through that, we can create a collaborative community where some of these preferences can be cross-matched so that we can work out what somebody else may be interested in. It sounds simple when you say it, but the mathematical complexity behind that to actually get even a 1% increase in a model. When companies employ data scientists, that's what they're actually doing. They're trying to squeeze that 1% extra out of a model, because that 1% extra might be £100 million of revenue if you can get a preference match to another user so that you can cross-sell. So principally, we can use the idea of ratings with collaborative filtering. Does a user like something? You know, what is their preference towards that? Have they rated this between 1 and 5? Have they given this a 1 or a 0? And then we can find similar communities of users so that these choices are no longer disparate. We can apply a variety of algorithms using collaborative filtering. And it's interesting because some of these offload the compute early on. Some of them do it at runtime. So you begin to have to get into a sense of, you know, what choice does my production system need? Am I able to do a whole bunch of pre-compute because I've got the data that I need, most of the data that I need now, or am I going to have to do this later on at runtime? In which case it's going to be much slower. We can rank. There's a phenomenon called KNN. So your nearest neighbor. So whenever you take these ratings, whenever you try to find similarities between either different groups of items that you're trying to sell to people so that you can cross-sell this, or groups of users, what we want to do is we don't want to process 20 million users. We only want to process 100 that are so close to each other where we can push those preferences. Otherwise, the amount of processing that we're going to have to do on that data set is going to be incredible. Then we have to think about the kind of data that we've got, that we're collecting. Are we collecting ratings data? Because with a website like Amazon, we can rate a book between 1 to 5. With Netflix, we can do something similar. We rate articles on Wikipedia, I think. We rate films on IMDb. And all of this information can then be used to suggest somewhere on the scale whether or not I would be interested as another user, because my set of preferences for those ratings are very similar to someone else's, so I can offer them the right choices. So that's explicit. I have this ratings information, but that's not normally what we get, is it? You know, if somebody's going to buy something, they're either going to buy it or they're not going to buy it. So we end up, in that sense, with just a binary choice. And that's a very, very different approach to being able to recommend, to be able to put a 1 or a 0 in a box. You still have to do that. You still have to account for the fact that somebody maybe didn't buy for something to really understand how these numbers fit together. Then we have to evaluate things. So it's interesting. On the demos that I'm going to show you, you'll see that when we talk about the model that we're building, we may inject things. We may inject things into this model. So, for example, if I'm running a clothes site and I get a whole number of SKUs, a whole number of sales items, am I going to want to take like dresses and then sell them to a whole bunch of men? No, we're going to have to build a model with some rules and exceptions that filter these kinds of things out. So we may end up with a whole set of rules to tweak this model, to shape it so that it's not one homogeneous glob of we're testing this thing for this set of users and this thing for this set of users. So So we have to apply these rules as well. And the closer that we hone into these rules, the more that model becomes accurate. So in statistics, we can test the efficiency of this model by testing the error value. Now, because we're not going through all the slides, I'll talk about this now. When we take these models, it doesn't matter how we do things with machine learning. We have this concept of training. Okay, we talk about building these complicated mathematical models. We don't do this anymore, right? This is how I can do this. I did study physics. I understand enough of the maths to understand it, but I don't need to do any of it anymore. The software does it for me. I give the software its rules. The software goes off and builds the models, and then I train this. So if I've got a large data set, what I want to do is I want to say, I want to build a model given this data. That's machine learning. We're letting the machine do this for us. How do we make the machine learn? Well, we give it a feedback cycle. Let's say we give it an amount of data. We then want to test this with new data to see how effective this is. So when we talk about training a model, all we're actually doing is letting the machine apply an algorithm or a set of algorithms based on our rules and based on our data. We put this through what we call training, and that will take maybe 80%, let's say 80% of the data set we use to train this model. We've built this model now. Then we can test it. Then that last 20% can then be used as a feedback cycle to say, can I predict, based on feeding in this previous 80%, what these users will be interested in? And that's the machine learning component. Okay, it's as simple as that. It's as simple as this feedback cycle, letting the machine do all the work and then feeding back into this algorithm. So in that case, I can test the error, can't I? Because at the end of the day, if I can predict all these data points from a model that I've created from training data, then the next set of data that I test, I can then test the margin of error against this. And so if I then take that margin of error as a mean, and I sort of extrapolate this out on a graph so that all of the distances between my predicted points and my actual points, because I've got that test data, then I can work out that mean square of error. Now, if that mean square of error is 0, does anybody know what that means? Yeah, it means that I've predicted everything absolutely perfectly. But that's never going to happen unless I understand completely how this model works with my data set. So this is how Amazon has such huge growth. You can see I've got a child in the house that watches Lego, Turtles, all the rest of it. But I'm a sci-fi fan, and it's picked up bits and pieces of things that I might be interested in as well. And I can sort of drill in, and I can look in and see who actually recommended this to me. So there's a whole sort of trail as to how these calculations took place on this website. So I'm just going to go through a couple more slides, and then I want to go straight into some demos just to show you what's possible. So there are a lot of problems associated with this. So, you know, it's not all roses to be able to plug these recommendation systems in and then just take this data set and be able to tell users exactly what they want to do or buy or try. We end up having a lot of problems, and we have to make decisions around these issues because there are some algorithms that make these problems a little bit more redundant. Some help them slightly, but you know, if you go down that route, then it may affect something else. So there's a lot of decisions when you actually get into how these work. The most common problem is called the cold start problem. So when you're building up a data set around recommendations, what you have to consider is that you've got this constant influx of new users, and essentially, even though this is great because you want a very, very dynamic system, you've got a problem called cold start, which means that there's no data or no crossover for these users. So how do you identify, even though there may be similarities between a particular user and another user, how do you identify what to cross-sell them? Well, it's really not easy at all. There's ways that you can extrapolate existing data, but you end up with a very, very common set of problems and ways to solve them, but you can't solve them perfectly. So it's entirely possible that new users may not get the recommendations that existing users get. So then you end up with this sparsity problem. So not enough data to rate items. If you have 20 million users or 200 million users, and you build a big matrix of all of these users, what do you get? Well, you get a whole load of gaps in this matrix. And it may be that this leads into other things, like this grey sheep problem. It's a funny term, isn't it, grey sheep? But these are users that are unlike any other users. And believe it or not, you find pockets of these all over the data sets. So you can't actually use a whole body of users to build recommendations because they're not like anybody. They're in clusters on their own. Then you have people potentially gaming the system. So I'm trying to think of a first-hand example. I can't. But you can rate products, and if let's just say you're an author, and somebody's got a competitive book on Amazon. What would happen if you get all of your mates to give them really, really low ratings? You know, would that affect the system? Well, of course it would. You know, and we know that gaming occurs in all of its forms. Stack Overflow and the sort of Stack Overflow examples are really, really popular around then. But you have a whole bunch of other things as well around labels, around invalid references, labeling. You know, you might have similar products that are called different things, and you know, even though you've got one set of users that are labeling, that are giving ratings for them, and you've got another set of users that are giving ratings for another set of products, and yet they're the same thing, but you can't use them within the system. And then last but not least, which I think is the most important one, is scalability. Right? This is a real problem. This mathematics doesn't actually scale well. You know, it's actually not easy to parallelize some problems. And when you deal with very, very large matrices in large data sets, to be able to factor them down into something that can be pushed to a particular machine, to a particular virtual machine, is very, very difficult. Okay. I want to take you through a journey of how these builds for recommendation systems work. You know, this is a recommender or part of a recommender with a high-level language called Pig, and Pig can be applied with HD Insight, Hadoop on Azure, and this is a real pig. Honestly, there's literally like about 20 pages of this to do the same thing that you can do with drag and drop in 20 minutes in AzureML. And you know what? There's actually no variation in the result because it uses the same algorithms. But I have to put this together myself, you know, with a cursory knowledge of Pig and SQL and all the problems of being able to distribute this across Hadoop clusters and have one node fail and take things. Okay, so this is how it starts. Then there's that same code, right? And this is Scala, and this was written for a framework called Spark. I haven't shown you the 20 pages of Pig, but that's the equivalent in Spark of that 20 pages. Okay? So now you can see that there's a consolidation of all of this activity into smaller and smaller code segments, so that you don't have to do so much work or understand what's going on under the seams. So, how many people have used HD Insight? Okay. I definitely predict that more of you will be using HD Insight in the next 6 months. So, I've already set up my subscription for HD Insight, and what I'm going to do is I'm going to run a batch of commands now, and this is going to set up a Mahout job, within HD Insight. I've submitted this to my HD Insight cluster. I'll talk you through a little bit of this. Right, so I've got, I'm using a data set, which is a public data set called Group Lens. This data it's all anonymous data, and I've got a user ID, I've got an item ID, and I've got a rating. So already I've got a system which has rated movies, and a timestamp here, and I need to find a sort of a way to take a whole set of item recommendations and then recommend them to a user. So you can see here what I've done is I've set up a Mahout job, and I don't need to show you any code because the way that I'm using this is intrinsic to Mahout. So I've given this a place where I can take in the data that you've seen, which I've already done some pre-processing on, because the input to all of these functions is user ID, item ID, and rating, or it's just user ID and item ID if I don't have that rating, so whether it's implicit or explicit. So what this is doing is it's running a machine learning job on that cluster over MapReduce, and it's possible that I can prove to you that that is actually the case. But there's so much going on in the background here. What you can't actually see is there's a collection of chained MapReduce jobs to be able to do this, and in order to actually split this up and cluster it, I've used something called similarity co-occurrence. So I've had a whole set of users, and I've built this very large matrix based on a cross join. So I've put users on one axis and I've put users on another axis, and what I've done is in the boxes in the middle, I've put all of the items that they have bought in common. And that's effectively what it takes to do this. And then I can build some ratios. Okay, so very, very simple maths, but then I can apply complex algorithms to score this and work out whether it's a good model. But in order to do this, I run this over a MapReduce job. So if any of you haven't done MapReduce before, a map will basically pull out all of the significant piece of information that you want, and a reduce will aggregate that information. So I want to form many key values. So I may have, if I'm doing a classic word count, I might want to count the number of words. In my map function, what I might want to do is every time I see a word, I emit the word as the key, and then I emit a 1 as a number. And then by the time it gets to the reduce function, I should get the word as the key, and then I should get a whole string of numbers that I can just add up. So in that way, I know, by building an item list within that MapReduce, I know that I can do this maths. And then Mahout will do this maths in the background. You can see that that data there's a 2 meg file there. Right, I've only got a two node cluster. So if I wasn't so cheap and I had a reasonable sized cluster, this would occur linearly faster. But the way this has had to have been done is it's used a bit of matrix mathematics, which I'm just completely masked from. And it should put the outputs when it's finished. It's still running, it's still running, it's still running. It's still running a MapReduce. It should put the outputs in blob storage. But you can see, I can create a cluster that's 500 nodes and do this 250 times quicker than I currently am, and then continually pipeline that and then use that within my site to build up these recommendations. Okay, so these things are possible at the moment, but I've got to use PowerShell, I've got to use Mahout, I've got to use Hadoop, I've got all these horrendous things that I have to know about. So I built, unfortunately, like I said, I can't do a demo. I've got quite a few demos prepared of AzureML. This is what it looks like. You have an ML Studio interface, and what it does is it allows you to build everything in a drag-drop. Can you see that at all? Drag-drop manner. So in terms of how this relates to Azure, I have a whole bunch of objects where I can just say, I've got some things in blob storage, I'm finishing an HD Insight job, I need to pull some information from SQL Azure. And then I can take all that, I can get it within the right format, I can split it up, I can put an evaluator to score something, I can build something so that I potentially get the outputs, which we're going to see hopefully in a second. Still going on, great. And as a result of all of this, I end up with these recommendations, but I haven't had to execute any PowerShell. I haven't had to write any code at all. I can tweak it, I can tweak my model, I can add some scripts, I can build up something custom, but out of the box it gives me something that I can put together in 20 minutes. And all I need to do is drag and drop all of these connections between them so that I end up with that familiar feedback cycle. So this is the direction it's heading in now. And this is completely tied to Windows Azure. So there we go, that's still going on. Excellent. So while that's going on, I'm just going to show you another thing, and that should take 5 minutes, and we should finish at 5 past. My whole ideology around this is, I want to show you the complexity at the moment in doing some of these things. It doesn't feel complicated, and if you're happy to learn all these frameworks, then fantastic. But when they made the announcement that machine learning is being democratized, it really is, because it's turning into something more scriptable and drag and drop away from the command line. Okay, so we finished that, which is great. Okay, let's look for that. Sudo. Here we go. Out. No. He thinks that's not the one. Aha, I remember, I called it output. Very cunning. Right, so here's the output. Okay, there you go. So you can see that what it's actually done is if we take the first user, you can see that it's built a list for that particular user of a whole set of items, and because I've got a rating scale of between 0 and 1, it's taken the top number of items that it thinks it can recommend me within the boundaries that I set with it. And I've also made this highly iterative as well. So I've let it do a number of iterations to sort of minimize the error count that I'm going to get, to try and get the highest number of. So I've had a slow execution, which all of you have seen, but I've got the highest number of values. So rating's very close to 5. And what it's done is it's looked at that whole user matrix of all of the people that have bought similar items, and then it's identified out of that the items that I haven't bought, and then suggested to me as user 1 what this is. Okay, so you can see that we can build very, very, even though we had to do a bit of work, not a huge amount of work, and we've been able to get some recommender data.